time series data which is based on capturing, say, temperature at regular intervals, and you want to predict the next hour's temperature based on previous few hours closing temperature. Similarly, you may use it for, in a retail scenario, you can use it for a example like predicting the volume of sales for a particular item, where suppose you captured the average sales every day, and you want to predict how it's going to look like for any future sales. You may use this kind of an architecture to help us understand the overall how the prediction can be done by creating an LSTM model to predict the overall sales in the future. But one issue that comes when it comes to modeling supervised learning problems in RNN is, it's great when we talk about modeling the what we call a sequence. But when we talk of modeling a sequence of sales data, modeling a sequence of stock market data, modeling a sequence of temperature, it's talking of one variable and the value of one variable across the whole spectrum. So here, it's very important for us to pay attention that a sequence typically refers to a univariate data. So to give an example, let's look at this data. It's called unit av2.csv. Let us see unit av2.csv. It's actually capturing a unit price, average unit price every day, every month, for consecutively many months. So you need to be very clear that while this is a univariate variable, how do you get it to a supervised problem? A supervised problem of prediction is basically a regression problem, right? Where you predict the output value given a set of input variable values. But here you are faced with a single sequence of data. So it is here that we bring in the notion of what is known as autoregression. What is autoregression? Autoregression is nothing but creating a regression problem from within the univariate time series. How does it work? It works by a simple phenomena like this. Let's look at the data again. Suppose we have a sequence of this. It's a continuous sequence. Now we model this as an auto-regression problem by saying that I think a sequence of 3 consecutive data points is helping us predict the 4th data point. So if you see, past 3 data points are allowing us to predict the 4th data point. So 1, 2, 3 become your input and 4th becomes your output. By cascading it further, 2, 3, 4 become your input and 5th becomes your output. 3, 4, 5 becomes your input, 6th becomes your output. So like that, now can you create a input output supervised learning problem? The answer turns out to be yes. The sequence length is something you can decide. You want to take, say, 5 at 1. Let's say 1, 2, 3, 4, 5 is determining the 6th, or 2, 3, 4, 5, 6 is determining the 7th. So like that, you can have your own length of sequence, which is determining to be the input string, and using that to predict the n plus 1th value is going to be your regression problem. And you can imagine if there are n data points, if there are suppose 5 is your length, you can have n minus 5 rows of regression equations. And this is what we call as auto regression modeling of sequence problems. When we do auto regression, it is important for us to specify what is that stride length, or what we call as sequence length, which we take as input. And this particular sequence itself, we model it as the output of an LSTM, which is internally trying to predict the output function relation between every 6th entry and first 5 entries, or every 4th entry and first 3 entries, then second 3 entries and the 5th entry, like that. You keep on creating n minus 3 in case size of stride is 3. You take n minus 3 rows. So you need to understand that in these kind of scenarios, it is very important to capture the original data in terms of a sequence of data, which is helping us determine how the LSTM is modeling the relation between data points in the same sequence. So the execution of this may take some time, but let's go through the code. So here what we've done is we just read the data frame. We use the first column, which is the price. And now what we're doing is we're scaling the data set with a min-max scaler. You know what min-max scaler is, right? Min-max scaler takes a specific data set, scales it to data points between 0 and 1. Then you transform the original data set with the corresponding scale. So we have a scaled data set between 0 and 1 as the corresponding input. Now here is what I want you to pay total attention. Let us assume the length of input for the auto regression we call as look back. Look back is the length of the input X, which we're using to model the next output value. So here in this loop, what we're doing is, let us take the point I randomly in the sequence, go from index I to I plus look back minus 1. That's going to be of length look back. That is going to be the input. That's what we're adding to data X. Then if you look at data Y, we're appending the I plus look back entry, which is the entry immediately after the look back minus 1 index, I plus look back minus 1 index. So at any point of time, I to I plus look back minus 1 is the input, and I plus look back is the output. That is one row. How many such rows will be there? The number of rows will be length of data set minus look back minus 1, because the first few elements, which are look back number of elements, will not be possible to be part of the output. They will only be part of the first row input. So the first output will start from index look back. So the total number of rows will be length of data set minus look back and the ith row will have element dataset I to dataset I plus look back minus 1. Then Y will be dataset of I plus look back. This is very important for us to understand because we are converting a otherwise a univariate sequence or a full series to a regression problem by this kind of an auto-regressive modeling. Why is it called auto-regressive? Because you are creating a regression model for the data within one sequence. So it is like you are trying to understand the regression dependency of the same data with a part of the same data, one part of the data with another part of the same data. That is why this kind of problems are very akin to modeling for regression in terms of a typical recurrent neural network architecture. Could be plain RNN, could be bidirectional RNN, or it could be LSTM, or it could be GRU. So this framework brings us to the way we can model any generic sequence problem into a corresponding problem of modeling the output of look back entry in terms of the previous I to I plus look back minus 1 entries as input. So once we give all of this data to our architecture, the architecture will create an internal model. Then comes the question of how do you measure the accuracy of such a prediction? This you can run it on the same sequence of data, and you anyway have the sequence of the earlier data, right? So based on your model which you have obtained, run it on the sequence of inputs which you already have, and you obtain the outputs and see and compare with the original data in your sequence. Suppose you had the fifth entry earlier and fifth entry you estimated from your model based on second, third, fourth data with look back 3. Then what you can do is you can compute the mean square error of difference between what you actually had original data and how you predicted. So your own data can be your indication of how good the model is, and that can be a measure of your hyperparameter tuning. Like, what is the hyperparameter you want to tune? What is the look back I will look at? Do you want to look at 3 data points determining fourth, or you want to look at 2 determining third, and so on, or you want to look at 4 data points looking at fifth one? So like look back is one example of hyperparameter you may want to tune the model. Then when it comes to modeling the exact problem, we have here modeled the overall prediction problem as a single hidden layer of 4 LSTM cells, and this is again a hyperparameter you can choose. As I said, I've chosen a single LSTM layer, 4 cells in that layer, and I've compiled this for the for the look back minus 1 data elements, 0 to look back minus 1 data elements, which I have created as input rows, and the corresponding outputs, which are single dimension arrays of the look back indexes. Then I let the training converge, and we see that there is reasonable convergence in 40 epochs with a convergence to a reasonably small error. If you want to increase, you can also increase. But finally, if you see what you're doing here is you are mapping the data within the sequence as the input and the subsequent data after the look back number of elements as the unit output. So you're trying to create a supervised regression problem out of your existing sequential data set, and you're trying to fit a single hidden layer neural network to manipulate the model which you have created, input output. Then what you do is you try to evaluate the prediction by looking at whatever was your actual original versus whatever what you are predicted, and see what is the overall mean square error you get in terms of what is your RMSE, which is square root of mean square error of whatever you predicted versus what you observed. So what I will do here is I will demonstrate a slight variant of this by changing little bit the number of epochs so that we see a better convergence with more epochs, so that we can see if there is a better convergence. I think we'll start again. So earlier our error was 0.14, if you remember. Let us see if changing the number of epochs is allowing us to converge to a much lower error. So you see that there's not much change in the error. Let's see even more. Let us say we put 100 epochs. So this is what is the experiment you need to try to look at. So not much difference. So we see the convergence is pretty much similar. So what, let me try to do this is, let me try to increase the number of LSTM nodes. So we see that even here it is converging at 0.054. This is probably the best. Now let's see what the RMSE gives. We're not seeing too much change in the RMSE, even though we are changing the architecture from 4 to 8 layers, 8 LSTM nodes, and we are feeding 100 epochs. So you see here what we've done is we've taken a sequential problem, converted into a supervised learning problem, and we have also made sure that we are able to capture the quality of the model by looking at the goodness with which it's able to predict the same sequence, which is what we're getting by RMSE. And we can actually change the hyperparameters by probably adding one more layer. I don't know if I should risk it because it may lead to a larger compute time, but let me try. Since we have some minutes left, what I want to do is I want to try out a one more layer if it is allowing me to do, and see if that adds any benefit. I think there is a issue because you cannot add just like that. Let's not worry too much about it. Basically, what I was trying to do was something like deep secret networks with multiple layers. So this was basically for a simple sequence prediction of data for any time series. It could be sales series, stock market series. So one exercise I want you to try is capture the sequence of OHLC data, which is open, close, high, low of a particular stock market. You can get it randomly from a lot of sites, stock market data for any script from NSE or from NYSE or anything. Then fit that whole data into this model and try to see how an LSTM model can be used for predicting stock market. Say, if you're doing O, use only open data. If you're using closed data, use only closed data. If you're using high data, use only high data. Or if you want to use average data across the day, you can use that also, high and low, middle. So you can use that for stock market prediction. This is one exercise you may want to try, which is fairly simple to work. Now, I just want to conclude by showing a slightly more extended application of the same thing for what we call as text prediction. So in text prediction, what we try to do is very similar to what we have done in the sequence model. Only thing is, what we do here is we capture the input as the set of characters of sequence length, and I to I plus sequence length minus 1 is your input, and the next chars, which is the output, will be I plus sequence length, which is the, in our case, the look back index value. So 200 characters, then 200 first will be the predicted value. Like that, you take the long sequence of text and convert it into a 201, 201, 201, 201, like that, of length of the data minus 200 number of data elements. Then we use the same LSTM kind of model to predict the sequence. Only thing is, here you got to understand that since we work on numeric data in sequence predictions, we do not predict character to character sequence. Instead, what you do is you look at all the unique characters in your text, and to each character you give an index. So if there are 59 unique characters in your data, so you give the first character, let's say A as 1, B as 2, then maybe D is present, then that becomes 3. So there are 59 values you give to each individual character. Then for each text character what is there, you replace that with corresponding number, which is the index. So you see here, we are talking about populating the data such that the index of that is captured rather than the word character being present, because there is no notion of predicting character sequence using LSTM. You can only predict numbers. And the numbers also, the way it is done is it is taken as a 59 dimension vector where all the values are 0 except the position of that character becomes 1. So what you do is you have each character represented by a 59 element vector, and you use this to predict the output. Again, the output is presented as a number which you output as the corresponding character, and you try to generate the LSTM model to map these sequence length number of input output combinations. As you know, each input is a tensor where the tensor is nothing but 200 number of input characters in input. Each character is represented by a vector of 59. So after such modeling, you give it to the LSTM. We have created a output here, which is hidden layer of 128 LSTM nodes. Then we're trying to compile, and at the end of it, we try to use this for predicting the output. So for example, suppose we have from the data, we created a small text. We take the first 30 characters and you try to predict the 31st character based on this. So if you look at the data here, we said consider diabetes a disease. The next character is most likely S. This is the next character it has predicted after disease. In this case, it's not able to predict so closely. So you see, it's not so accurate in terms of the predicting the next character, mainly because you can imagine the accuracy here. Finally, when we're closing, it is about 41% accuracy. So one thing you got to be very worried about in LSTM architectures is they're not like CNNs where you get very high accuracy. So you have to be really careful in terms of modeling your data and running maybe multiple layers of LSTM or large number of LSTM nodes in order for us to get a reasonable output in terms of the accuracy. So what we saw here is two categories of applications. One is the most common application, which is basically a straightforward sequence prediction problem using LSTM. And then we have a similar approach for text prediction, where since it is about numeric prediction, what we do is we treat this as a tensor prediction by looking at number of characters present and giving a number to each character and predicting the output tensor or vector in terms of the input vector. So it's not like text prediction is possible on text character. Instead, you convert text paragraphs into text tensors based on number of characters present, and you model this as a simple autoregression, but each data point is a vector rather than a character. So here is another example of a bidirectional neural network where we try to create a neural network layer with a bidirectional RNN, where we have used a basic LSTM cell as forward and basic LSTM cell as backward. So this is a bidirectional LSTM, and we have used the raw gradient descent model. And what we've seen is the final accuracy is close to 90% in terms of prediction. So this is the example of the bidirectional LSTM. So you can imagine here what we're talking about is forward cell as LSTM, backwards as another LSTM, and using that to predict the output class. So while this is a bit more involved, but what I would like to look at is you getting comfortable with at least this program, which is any sequence prediction in terms of LSTM. That's the basic idea of teaching you the variants of RNN. In any of these cases, you must have seen that I have not used plain RNN because plain RNN is very much useless because of the vanishing gradient problem. So unless otherwise specified, whenever we talk about RNN, we will typically talk about a LSTM architecture. With that, I kind of would like to